All right, let's go ahead and take a look at another example. So this example here says that suppose you have a random variable x, which you believe to be binomial. So that's pretty important. Remember that x is just whatever object you're interested in. So let's make that in red. So I'm looking at result here from this random variable, and I believe that it is binomial with n is 4 and p is 0.3. So I'm taking samples of size 4, and I believe the probability of a success is 0.3, so 30%. And so then x is basically the number of successes. So it makes sense that if I'm looking at 4 individuals, there could be 0 successes, 1 success, 2 success, 3 success, 4 successes. So these are the possible values of my random variable. And then it says I conducted 1,000 trials observations and obtained the results summarized on the table on the right. So notice that the results that I see here observed, that's from my sample. So I don't want to pay attention to this just yet. So let's kind of ignore that. Because remember, we want to take a look at the expected. So how the heck did they get this expected thing? So I did want to talk about that because notice that in previous problems, for example, I gave you the probability of success, but here we don't have that probability of success. So let's kind of see where that comes from. All right, so it says determine the chi-square test statistic, the degrees of freedom, critical value, and test the hypothesis. So here's the hypothesis that the random variable x is binomial with n is 4 and p is 0.3. And I just want to demonstrate that if you go ahead and use the calculator, because we know this is binomial with n is 4, and the probability of success 0.3, then you get to visualize the random variable. And if you set this equal to, let's say, 0, you get the probability of success. So that's 0.204, 0.2401. The probability of success here, so is 0. Again, that gives you the probability. So it's really important for us to know that the null hypothesis actually does give me the probability of success. So I can go ahead and write the probability of category 1. So that'll be 0.2401. And remember that I got this by looking at the probability that my random variable x is actually 0, just using the binomial calculator. Similarly, I can go ahead and find the probability that I get a 1. And we see that it's 0.4116. So that's how I get these probabilities. So again, it's the fact that they're telling me that this variable is binomial that we can use to find the probabilities. And once we get the probabilities, we can then go ahead and find the expected values, because I can go ahead and use the formula that the expected count is equal to n times pi. So n is your sample size, which we know to be 1,000. They told me right here. And then I simply multiply that with the decimal on the left-hand side, and I get these values. So here's the expected count in category 1, expected count in 2, expected count in 3, expected count in 4, and in 5. And remember that all we're going to do now is we're going to use stackers to help us evaluate the level of agreement or disagreement between these two columns. So we got the observed, what I actually got from my sample, and we've got the expected count, the theoretical values, if the random variable really does follow a binomial distribution with these parameters given. So notice that there's not very good agreement here. 260, 240, that's a gap of 20, 400, 411. That's kind of close. 280, 260. So yeah, we're probably going to reject the hypothesis. Let's just go ahead and show all of the work. So we've got the null. Let's just do a hypothesis test, go through all the motions. So hypothesis done. Let's go ahead and check the requirements. Remember, the requirements are that we need a simple random sample and independent. So these are going to be pretty self-explanatory. Then there's the two special ones. So let's emphasize those. Let's make them purple. The two special ones are going to be the expected counts. So condition 1 is that all of the expected counts got to be greater than 5. And I'm just going to greater than or equal to 5. I'm just going to check that off because you're using your eyeballs Go through these expected counts here. Look at them. They're all bigger than 5, so I'm going to check that off. The other one is that no more than 20% of the expected counts can be less than 1. So just look at them again and tell me how many, like what fraction do you get that's less than 1? So bigger than 1, bigger than 1, bigger than 1, bigger than 1, bigger than 1. They're all bigger than 1. So 0 out of 5 categories, 1, 2, 3, 4, 5, are big, which is 0.0. And that's definitely less than 0.2. All right, so we meet this condition also. We don't have any categories less than 1. If you do have categories less than 1, just count them and look at the proportion and just look for that proportion being less than 0.2. We'll see an example later on about what happens if that's not true. All right, anyway, let's continue because we've met the requirement. So notice I'm just going down this little checklist, right? We got the hypothesis. I've got the requirements, the conditions for my test. And now I just need to go ahead and sketch my distribution, find the critical value, and then the test statistic. All right, so my distribution, because I know that I'm checking whether this random variable, anytime you've got this, again, expectation and sample in a table format, we're going to go ahead and do a chi-squared statistic, and it's a right-tailed. All right, and degrees of freedom is always k minus 1. K is the number of categories. So for binomial random binomial random variable, whatever n is, you add 1 because of the 0. So there's 5 categories, right? K is 5. And when you subtract 1, we go back to 4. All right, so then I can go ahead and find chi-squared of alpha with 4 degrees of freedom. So you stack crunch for that. Four degrees of freedom, right-tailed is 0.5. All right, 9.4877. All right, there's our critical value. Remember that this is the level of disagreement that we must exceed before we can say that, oh yeah, there's too much disagreement, so my sample doesn't seem to be, agreeing with that expectation. So let's go ahead and compute the test statistic and the p-value. And remember that the way to do this is you type in your expected and observed into StatCrunch, and then you just do a chi-squared test. So let me write that down. All right, so I already have this saved. So let's see, this is from our first example, observe binomial. So I titled it binomial so that we know it's the binomial distribution here, and you can just compare your table. This is the same table here. Okay, so 260, 40, all the way down to 10. Is that correct? Yep. And then the expected here in binomial. All right, so let's go to stats. And I'm going to go to goodness of fit. Oh man, did I write the wrong thing down? Yeah. So it's going to be stats, goodness of fit, then chi-squared. So where is the observed? So I'm going to click observe where it says binomial, and then expected where it says binomial. And that's pretty much it. Compute, and you get your test statistics. So we can see that they summarize the results for us here, and we've got our test statistics on this column. What the heck? Anyway, here are our test statistics. So let's go ahead and write those down. All right, so what is our conclusion using those test statistics? And it was 11.98. That's bigger than 9.4. So we're landing here in the rejection region, critical region. P-value is 0.01, so that's less than alpha. So again, the conclusion is that we're going to reject no. So in other words, my sample, the blue data, does not seem to agree with, the orange. So therefore, we're going to go ahead and reject the null. We have sufficient evidence. Well, let me not use alpha just because we're trying to make this an English sentence. At the 0.05 significance level, to say that our random variable, I was going to put X, but again, we're trying to use English sentence. Random variable is not a binomial random variable. With those parameters, n is 4 and p is 0.3. So it could be binomial with other parameters, but not with whatever they described. All right, cool. And that basically summarizes our example. So you can see how quick this actually is. Most of the work is just in the checking the conditions. So let's try another example. All right, so again, the problems themselves will give you the sample, but ignore the sample for a second. So here's the next example. According to the manufacturer of peanut M&Ms, some of the best M&Ms there are, in one bag, there should be 12% brown M&Ms, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. You buy a bag of peanut M&Ms and count the number of different colored M&Ms. The frequencies are shown below. So off to the side, we see the frequency. That's my sample information. And I want to test if the manufacturer has correctly advertised these percentages using the 5% significant level. So notice that we are actually told what the probability of a given color is. So I guess we could put that in here, PI. So the probability for a brown M&M, that's 0.12. For yellow, that's 0.15, 0.12, 0.23, 0.23, and then 0.15. And then what we can do is we can go ahead and find the expected count. So the expected, remember, is simply equal to the number of total M&Ms times the probability. So first you got to go ahead and get the total. And just like in chapter, when we 2 and 5, we just add up all of the frequencies, and you'll go ahead and you find that there's 400 total M&Ms in this bag. Wow, that's a lot of M&Ms. All right, so if you take n times pi, you'll get the expected count. I've already done it, so you guys can go ahead and try this here. But for 12, that's 400 times 0.12. You'll get 48. And then 400 times 0.15, you'll get 60. So 0.15, that's 60. And then 400 times 0.23 is 92. All right, so the question is, if this is the expected count for every category, every color, does this count tend to agree with your observations? So notice 53 versus 48, 66 versus 60, 38, 48, 96, 92, 88, 92, and 59, 60. There's pretty good agreement between these numbers, right? They're all pretty close to one another. So if we go ahead and now do our test, then I wonder what we get. So let's go ahead and complete this test. Notice we got to complete the test, so we're still missing the hypothesis. So let's run through these motions. So number 1, hypothesis. So what is your null hypothesis? What is the alternative? And it always just go ahead and mimic the language that they tell you. So to see if the manufacturer has correctly advertised these percentages. So we're going to say that the M&Ms color distribution follow the advertised you could say frequency or percentages. The alternative is that the M&Ms do not. The advertised percentages. All right, then we got to go ahead and check the requirements. So I'm going to skip the SRS independence. Remember that for goodness of fit, it's whether the expected counts are all greater than 1. Oh, sorry, greater than 5. And no more than 20% are less than 1. So you just use your eyeballs for this one. You scan, literally scan your expectations, and you count how many of them. Just check that they're all bigger than 5. Yes, they are. And then let's count how many of them are less than 1. So there's 0 of them less than 5. So we meet this one. I think I said that wrong. 0 of them are less than 1. All of them are bigger than 5. All right, let's continue. Do the last test. So we got hypothesis, requirements. So the last one is my distribution. So how many categories are in there in this case? 1, 2, 3, 4, 5, 6. So we could do our chi-square distribution. We're always going to be doing a right tail test. And the degree of freedom here is 5. So go ahead and find the critical value. All right, and then I'll let you guys go ahead and do the same thing as before. So go stats, goodness of fit, chi, select the appropriate value. So I've already got them in my notes here. So that would be for the M&Ms. And you should find the following statistics. So the chi-squared value is 3.5 and the p-value is 0.61. So you can see that the level of disagreement here is actually very minimal. We don't exceed the value given to us, so we fail to reject the null. All right, and so here we go. You can see that this is the example where we're given the probability of success for every category. All right, so we got 2 examples. Let's do one last one. All right, so our last example has to do with so a supervisor at something called Fast Track Professional Temporary Services Incorporated suspects that her employees are more likely to call in sick on Mondays and Fridays than on the other days of the week. So I guess if you call out on Monday or Friday, you get a longer weekend. So anyway, they suspect that that's more people are calling out sick on those days than on the rest. So to test this claim, she collects data on the number of people calling sick on each day of the week. Her data are summarized in the following table. The question is, does it appear that absentees are not equally distributed across the 5 days? And so the key here is to see equally distributed. Equally distributed is going to happen a lot in our example. That's basically this first scenario where we went ahead and we said, if the parameter is known, then, for example, when I roll a die, I know the probability of each category is 1 out of 6 because there's 6 categories. Or for example, when I was asked to select a suit in a deck of cards, then the probability of success for any category is 1 out of 4 because there's 4 suits. Here, if we're assuming that the absences are uniformly distributed, equally distributed, then we're going to say the probability of somebody calling out on Monday, Tuesday, Wednesday, Thursday, Friday should be equal. So this is going to happen a lot whenever you guys see that. This is going to be the equally likely hypothesis that every day is just as likely for somebody to call out sick So the probability of calling out sick on a given day, PI, is going to be equal to 1 out of 5. So that tells me that the hypothesis that somebody calls in on day number 1, day number 2, day number 3, day number 4, day number 5 is 1 out of 5. And that's pretty much it. That's the only difference. The alternative hypothesis is that not all the probability that this is not true. Not all of the PI are 1 out of 5. So in other words, it looks like, for example, Friday and Thursday are higher. So that actually is captured by just saying they're not all equal to each other. Now, what we could do is under the null hypothesis, we could actually compute the expected count. So how many people did we expect to call out sick on each of these days? Let me just quickly show you guys how you can do this. So if all of them have a probability of 1 out of 5, remember that we just add up how many, what our sample size here is by adding up all of this, and that's 47. And then we take 47 and multiply that by PI, which is 1 out of 5. And I believe you get 9.4 for all of this. Now, because this happens a lot, right? Equal distribution. There's actually a very easy way to get this in StatCrunch. You just go stats, goodness of fit, chi-squared, and where it says observed, select your observed. So here's days absent. Now notice expected, there's this little thing that says all cells in equal proportion. So this whole little fact where it says all cells in equal proportion, that happens often enough that there's a special command for it. So again, that happens whenever you've got this equally likely hypothesis. So if you just click that, you can press compute and StatCrunch will find it for you. And we've also got the chi-square statistic and p-value. So that's actually the only thing that changes in this example. Everything else is exactly the same. Okay, so to summarize, the last kind of problem that you guys will face is when you've got this equally likely hypothesis for every category. All right, so hopefully this was good, and you guys can try out the homework problems.